Okay. Hi, I am Olivier Alla, not Ananour Ali Moulati, aka Alanour, as we like to call her, and emphasizing that I am presenting on behalf of her. It's her work. So let's get into this business of the water in subcontinental lithospheric mantle, which have been mostly dominated by the nominally anhydrous minerals, the NAMs. And in fact, in the next minutes, 10 minutes or so, I want to step back from this statu quo and just kind of remember that before NAMs, the hydrous phases, such as amphibole or phlogopite, were ruling the world of water in the mantle. And as we are here, let's also get back, step back again and reflect on the distribution of trace elements in the mantle assemblage. It's a long time that we know that the main silicate, the lattice of the main silicate, the NAMs, are not hosting all of the budget of trace elements in mantle. And we know that inclusions in the grain matrix, but also what has been called the pervasive grain boundary and interstitial components are major reservoir for incompatible elements. So the grain boundary and interstitial components, because it's a bit long, I will call it GBIC all through. So if we think about it, water is also an incompatible element. Therefore, water in a mantle must be more than NAMs. Okay, so to assess the distribution of water into the assemblage of the mantle, what we need is to analyze the auroch, the lattice and the grain matrix, the metasomatic phase, in our case it will be amphibole, and we will deduce the GBIC by just simple subtractions. So to do that, we use two techniques, the Fourier transform infrared spectroscopy and the simultaneous thermal analysis. So FTIR is well known. It's used by many to determine the amount of OH bound in silicates, or in minerals, sorry. But however, it's not the case of STA. So what happened in STA is that you measure the loss weight here, then you have information through the DSC, so through the calorimetry, about phase change or phase transitions. And at the same time, when you hook it to a mass spectrometer, you can see what kind of elements you are extracting. And you are doing that as you increase, the temperature continuously from ambient temperature to 1250 degrees. So the samples are basically large, fresh xenoliths from hosted in alkali basalt from worldwide area, and we define a wet suite which contain amphibole, and of course a dry suite which do not show any amphibole. After that, otherwise, these samples have the fertility range and the metasomatic characteristics that has been described for all the subcontinental lithospheric mantle worldwide. Okay, so what do we see? First, the water content of the auroch here is going from 500 to 5,000 ppm. And as you may see, as you may see on the thermograms on top, when you have a dry samples, it's basically the most of the water is extracted between 200 and 800 degrees, while when you have a wet samples, you have an additional peak at 1050 degrees. The things that I want to emphasize here is that we have a good correlation with amphibole about water content, and also the water content is correlated to the concentration of trace elements, of incompatible trace element, and here you see cerium, but it's correlated to many others. So yes, so that means that first, the strong correlation indicates that water abundance in the auroch is not due to secondary process or weathering, and second, that water is indeed behaving as cerium, at least at the auroch scale. Another thing that you can picked up on this graphics is that, in fact, you have only water enrichment, significant water enrichment, when your amphibole modal abundance is going way over 5 volume percent. So the analysis of the nominally anhydrous minerals by FTIR is basically giving you the same kind of distribution and water content that everybody has published in the last 20 years. The rock, the reconstructed rock, give you water abundance between 20 and 100 ppm. It will go to 130 ppm if you use the Bell calibrations. And it's broadly related to the abundance of pyroxenes, therefore fertility. Otherwise, the relationship with other index are pretty poor, and you cannot, for example, that the on your what is that right? The bottom right, that the cerium relationship with the water is much worse, or in fact, it's not as good as the ones that we got at the OROC scale. Okay. Now, amphibole. So amphibole has very characteristic thermograms with this huge peak at 1050 degrees. Yes, 1050 degrees. And what you see here is that the water content in amphibole are varying from 0.8%, 8,000 ppm, to 1.4 weight%. And in fact, this kind of value are characteristic of pargasite in the mantle, as you can see on the literature review figures here. And what it does mean is that most of, and it's of course nowhere near the 1.82 weight% that you would expect from stoichiometry. And that basically means that most of the mantle amphibole have undergone dehydration and oxy substitutions. Okay, so one of the key results of this study is that water abundance in NAMs are not correlated with amphibole occurrence. And that whatever technique you use, FTIR or TGA or STA. Okay, and although this kind of feels surprising because the hydrogen diffusivity is very quick, you will expect that one way or another, the NAM will recognize the occurrence of amphibole. And if you look at the literature data, here mostly FTIR data, you see that there is no difference between amphibole or even phlogopite bearing samples and dry samples. So in the end, the conclusion is that water abundance in NAMs are irrespective of occurrence, abundance, and composition of hydrous phases, of coexisting hydrous phases. Okay, so now that we have characterized all the components of our mineral systems, let's see how the water distributes between these various components. So if we look at the silicate lattice, which is the NAMs as measured by FTIR, you will realize that they only represent 6% of the bulk water of the rock. If we now move to the grain matrix as measured by silicate fraction by STA, and therefore which includes the silicate lattice, we are reaching in average 20% of the bulk rock. So that means that we have a difference that the bulk NAMs are basically 3 to 7 times higher than the lattice as measured by FTIR. So this discrepancy between these two measurements is not in fact that surprising, because we are not looking at the same site and at the same speciations. Indeed, when you are measuring mineral fractions, of course you will include melt inclusions and fluid inclusions. They could be micro or nano, and that will contribute to the bulk water of the GM of the grain matrix. But also FTIR is speciation dependent. So that means that with FTIR you are measuring OH, which is calibrated, and although you may detect the presence of other species of H like dihydrogen or molecular water, it is not calibrated and therefore not quantified for water content. So that will be about good. Amphiboles occur, when amphibole occurs, it may represent 95% of the water content of the rock. That depend entirely of this model analysis. But if you are in a case of a dry, not amphibole bearing or not trogopite bearing peridotite, then the GBIC will represent, in average, 82% of the rock water. So that means that the GBIC is the main reservoir of water. Okay, so although amphibole does not have any noticeable effect on the water content of NAM, however, it strongly reduces the amount of water in the GBIC, as you can see on these diagrams where you have a negative correlation between the percentage of water stored in the GBIC and the modal abundance of amphibole. That means that amphibole crystallization is drying out the GBIC. So that means also that metasomatic minerals and GBIC are competing for water and possibly other volatile and incompatible elements. That also means that we need to reassess our view of modal metasomatisms. Indeed, it seems to be more hybrid processes between the classic imported added metasomatic addition and some kind of metamorphic remobilization of previously existing components which were being stored in the GBIC. Okay, so rushing to the conclusions, I think that by broadening the scope of a study and by changing the tool that we use and shifting our focus out from the NAM, we reveal a new systematic, a new vision, I would say rather a new vision of the distribution and the content of water in the mantle. Yes, water in the mantle is more than NAMs. And here we are on a classic street light effect or street light tail. GBIC and metasomatic phases are key volatile reservoir and they compete for both volatile and incompatible elements. Now, if we consider the bulk assemblage of the mantle, meaning the GBIC and the NAMs, then your water content of the subcontinental lithospheric mantle shifts from a mere 200 ppm to something about 1,500 ppm, which is indeed much more than what one would expect in a depleted mantle. But the subcontinental lithospheric mantle is not a depleted mantle. There is hundreds of studies which show that the subcontinental lithospheric mantle is a refertilized depleted mantle, but it's refertilized. So this new finding have a potentially key consequence for petrophysics and geophysics. I think I don't have the time to go through, but I will be happy to answer the question. And therefore, to sum it up, I think that the dryness of the subcontinental lithospheric mantle, the alleged dryness, is basically related to a preconceived or misconceived idea that the subcontinental lithospheric mantle is depleted in incompatible element and therefore in volatile. And second is due to an investigation bias focusing on NAM only and not willing to get the full assemblage of the mantle. So that means that in this new framework of Earth, the mantle, the subcontinental lithospheric mantle, become an old, botoxed mantle infiltrated by metasomatic agents which are frozen in, which means that the subcontinental lithospheric mantle become a very important reservoir, but also a very important buffer for the exchange of volatile between the deep earth and the exosphere. I'm finished.
Thank you. We have time for questions. If anybody has any questions, I'll ask one myself. Yes. If grain boundaries are a significant host of water, what happens when grain size increases?
That's excellent questions, and it's something that we are working on it actually. So there is two possibilities indeed. Either the concentration of, as you may see, the concentration of water in grain boundaries is the lower diagrams here have kind of a slack. So in theory, you can go to very high content of water. So the reduction may increase the concentration in the grain boundary, but it's still need to be checked.
Thank you. Okay, it doesn't look like there are any questions in the chat. Oh, there's a question. Please step up to the microphone and introduce yourself if you have a question.
Okay, John Adam, Macquarie University. Do you find any glass in your samples? Any glasses in the xenoliths that you're studying?
So often occurring around amphibole, as everybody knows, you have glass, disequilibration glass or melting glass. As glass as itself, away from amphibole or in dry samples, no. But again, all this, is why I call it grain boundary and interstitial component. That means that you may have other phases. For example, I remember a paper of Bodinier which found a lot of micro phases like rutiles and phlogopite in the interstitial media, which were not really obvious at the beginning. So I cannot exclude the occurrence of glass, but as far as optical and even BSC imaging goes, we didn't find any.
Okay, well, thank you for your talk.